Thank you all again for being here today. Thanks for hanging in there. We're getting there. It's almost beer 30. Sure, Kevin's got everyone primed now. This one's only about 20 minutes. Hopefully we'll catch up a little. For those who don't know me, again, my name's James Dillon. Everyone calls me Jamie. I'm a graduate research assistant in the Sub-Zero Research Lab at the Civil Engineering Department at MSU. Excited to be here today for a variety of reasons. First, it's just an honor, and thanks to GNFAC for putting this on again and for having me. Second, I basically just finished this analysis like 3 days ago, so I'm excited to talk about it and hopefully get some feedback. Last of my various papers and projects, they're pretty much all locked away in the laboratory. This is the only one where I got to go outside and play, and it's inherently more fun to talk about. So, without further ado, mapping and modeling a glide avalanche with terrestrial Lidar in Glacier. I like to start with acknowledgements. I'll shout out Kevin, who's my advisor. He's made all these opportunities possible for me and has been a terrific friend and mentor. Thanks, Kevin. The whole Going to the Sun Road forecasting crew, Eric, Gabby, Zach, Keith Williams at UNAVCO was instrumental in showing us how to use the Lidar in the first place. Perry and Mark over at the SLF in Switzerland have been a great resource for RAMS modeling. I would have filled that bottom row out with John, who was another Sun Road guy, but instead a little shout out to my co-pilot there, who was a very good sport on these data collection trips. In terms of funding and resources, I want to particularly highlight TARP for funding me for several years. We'll begin with a brief outline. We'll start with motivation. I doubt I need to sell this group too much on the need to study avalanches, but we'll set the stage a little. We'll talk about background, particularly LIDAR and RAMS modeling, objectives, our study site, the Haystack Creek drainage on the Going to the Sun Road, our LIDAR scans, the pretty maps we made with them, how we fed those into RAMS, and then we'll conclude. So our primary motivation for this project is the threat that avalanches pose to roads. So many industrial, like mining roads, mass transit, like Teton Pass, some of those highways in Colorado, or recreational roads like the Sun Road, transect large avalanche paths. So forecasters have to balance health and human safety with the economic losses of closing a road, or in the case of the Sun Road, delaying plowing operations and its eventual opening. I'm sure it's less of an economic balance with a purely recreational road like the Sun Road, but still the idea is to get it open as quickly and efficiently as possible. Many of these roads, forecasters deal with the threat of large wet slab and glide avalanches in the spring that are difficult to predict, right, because they fail during non-extreme conditions. The biggest questions arise are, when will these fail? To which a lot of work has been done. Eric Peisch up on the Sun Road has published a number of papers linking meteorological conditions to failure days, basically. Some of these guys, Vera Valero and Weaver over at the SLF, are using the snowpack model that some of you might be familiar with to try to predict exactly when water is beginning to percolate on certain weak layers. The other question is, if they fail, can they hit the road? Towards the latter, that second question, what I'm presenting here today is a synthesis of LIDAR, terrestrial laser scanning, I'm just going to use those interchangeably, and avalanche dynamics modeling in RAMS. This figure I stole from one of Eric's papers back in 2012. This is the Going to the Sun Road, and you can just see all the large paths that it transects. The little blue star that I put up there marks our study site. We'll talk more about that in a minute. Next, a little background on LIDAR and dynamics modeling. I'm sure most folks here have some familiarity with LIDAR, but briefly, LIDAR units emit rapid pulses of light, and they record the strength of the backscattered signal and the duration of travel. Each point, or return, has coordinates x, y, and z, and a return intensity value. Most importantly, we can collect millions of these points in minutes from several kilometers away, far from the danger of the avalanche path. Using these, we can make a bunch of different maps. We can make digital terrain models, like the top one there. By differentiating those, we can make maps of slope or aspect. Perhaps most importantly, by taking the difference between a snow-off DTM and a snow-on DTM, we can make really high-resolution maps of snow depth, like that third one there. And we can also look at reflectance. We won't here, but we can. I want to circle, but this is a preliminary data set from the Yellowstone Club. I just want to highlight that snow depth map. We can see a lot of key, typical features, right? A lot of piling up of snow in the gullies, not a lot of snow on the cliff bands. Any guesses as to what's going on with that large red void region to the left? I feel like there are a few YC people here who probably have an idea. That was, what was it, 2020, the COVID year, when there was a large wet slab that was social media famous that failed at the ground interface. And they let us scamper up and grab a scan of that afterwards. And I think that's neat. In the Avalanche world, TLS is primarily used to evaluate snow depth and variability in release areas and changes in depth surrounding certain events, like storms or before and after controlled or uncontrolled avalanches. Perhaps the most popular work on this was done by one of my committee members, Jeff Deems, at Arapahoe Basin back in 2015, where he just made a number of really compelling maps of snow depth and change in snow depth before and after control events. Regarding avalanche dynamics modeling, perhaps the most popular one is the Rapid Mass Movement Simulator, or RAMS, developed at the SLF. RAMS solves the mass and momentum balance in a simulated avalanche based on a depth-averaged hydrodynamic system of equations. Admittedly, if you ask me too many questions about the physics behind RAMS, I'm going to run out of answers pretty quickly. Those are pretty dense papers, but very generally, RAMS will ingest a terrain model, information about the release area, most importantly, the average depth in the release area. That dictates the volume in the avalanche. That's perhaps the most important parameter. Some snow cover info about forested areas that might restrict flow, etc. And it'll output, most importantly, the runout extent, the flow and debris height, velocity, pressure, a number of other parameters at discrete time steps. This is a pretty example that I stole from Alpine Solutions online. So theirs look nicer than mine. So moving into our objectives, we have terrestrial laser scanning, which produces high-resolution maps of snow depth and changes in depth. It's not useful on its own for predicting runout extent. We have RAMS, which does predict runout extent, but has caught some flack over the years. It often suffers from inaccurate input data. Again, the most important input is probably the snow depth in the release area, which we usually just have to ballpark, right? It's usually too dangerous to actually access these areas and measure, and that causes a great deal of uncertainty. It's also infinitely tunable. RAMS Extended now has like 30 input parameters. By tweaking these, you can get any result. You can get an avalanche that breaks and then just stays still or runs forever, and anything in between, which is not particularly useful for predictive forecasting. So what we propose here today is a synthesis. We're going to use our really high quality, high accuracy TLS data as inputs into RAMS to reduce that uncertainty. And then we're also going to use our observations of the runout extent, also from our Lidar maps, to validate and tune the model. So to list our objectives, we aim to collect TLS data specifically surrounding a large glide avalanche event, of which there are many on the Sunroad. We're going to create maps and quantify parameters like release depth, deposition volume. We're going to use this data to input into RAMS and hopefully with minimal tuning recreate the avalanche. And then we're going to go a step further from a predictive standpoint. We're going to use this newly tuned model and try to determine how deep the snowpack would have to be for a road impact. It's all outlined in this flow chart that for the sake of time I'm going to gloss over because we're about to talk about it all anyway. So our study site, again, is the Haystack Creek drainage along the going to the Sun Road, which usually features a glide avalanche annually. This also is not my picture. I stole this one offline, but I wanted to include it because that lower red arrow there points to one of the plows that's clearing the road, which just kind of gives you an idea of the scale of this terrain. You guys probably all biked the Sun Road or something before, but it's huge. That red top arrow points to our release area, which is on Mount Gould. It sits at about 2,430 meters, the road about 800 meters beneath it. It's hard to see in this picture, but the key feature of this terrain is that in the middle there's about a 400-meter long bench in the center where the terrain is consistently less than 20 degrees. So basically it goes steep, flat, steep again. Whether or not the slide makes it to the road on any given year basically depends on whether or not it can clear that bench. Because this is the Sun Road, we have an excellent record of all these events. We can see in that table there, most years it doesn't quite make it over the bench. The exception is that shaded gray row. In 2020, it did impact the road. 2022, when we were out there, it stopped just short of it. We have a number of metrics there, R&D values. We have estimates of max crown depth and average crown depth, although I want to asterisk those. Those are just like visual observations from what I gather from the road 800 meters below. But it does give us a general idea of how big it ran each year and whether or not it hit the road. This is just a more GIS-y look at it. And again, in 2022, when we were out there surveying, it like just got to the edge of the bench, but didn't quite drop into that last waterfall portion and hit the road. So moving into our Lidar scans, we went out 3 times, 4 actually, one just didn't prove useful, but we went out the 17th of May once glide cracks started emerging before the slide. We went out June 3rd, shortly after the slide occurred, and then we went back in the fall to get a snow off scan. We know the slide released the evening of June 1st. We also know there was no precip between the evening of June 1st and the morning of June 3rd when we were able to get back out there, which makes things a lot simpler, fortunately. In the image up to the top left, we can see both a picture and a point cloud look at the release area after it failed. The beauty, again, of LiDAR is we can not only visualize these things, but we can also quantify them. So for instance, looking at the pre-failure scan, not shown here, we know that the average glide crack width was about 1.25 meters, and the max was about 2.25. We know the release area was 95 meters wide with an average depth of 3.3 meters and a max of 7.2 meters for a volume of over 25K cubic meters. So quite a bunch of volume for a relatively small pocket, at least relative to the whole size of the bowl. Conditions we know from nearby pits were typical of a late spring snowpack. We had brownie grains, melt forms, lenses, wet snow. Yeah, spring in the Alpine. So taking a look at some of the different maps we made, again, perhaps the coolest thing we can do with TLS is by differencing snow on from snow off digital terrain models, we can make these really high resolution maps of snow depth. I'll direct your attention, I do have a pointer. I'll direct your attention to E and F, that's total snow depth on May before the slide and June after the slide. In both, what we can see is extreme spatial variability in snow depth, anywhere from 0 to 8 meters. The little blue arrow points to our release area. We can see it's there in May, and then we see this big void oval in June because it slid to the ground, as a glide avalanche does. Perhaps the most compelling map is that change in snow depth up in D here, and we'll take a closer look at that in 3D. So again, what we're looking at in the map here is the change in snow depth before and after the glide avalanche. So red represent reductions in depth, green represent increases, that yellowish green is where it stayed about the same except for settlement. So we can see 3 distinct zones, right? We can see our release area, then we can also see this huge entrainment zone where it dredged out a ton of snow on its way down, and then we can see where it deposited and it just barely got to the edge of the bench but didn't quite spill down into the road. Again, we can quantify all this too. So we know that the average entrain depth was about 0.7 meters, and it entrained a volume of upwards of 65,000 cubic meters, which is neat because that's almost like 3 times as much as was in the release area. So a lot of the mass in this slide was actually from entrainment. We know the average deposition height was 3/4 of a meter with a max of just about 4 meters for a volume of just under 60,000 cubic meters. If we assume some densities, we can do a mass balance analysis. So we assumed a density of 350 kilograms per cubic meter in the release area. That's like a bulk snow depth over the whole 4 meters or so. And an entrained density of 250, which is like the top meter or so. We know this, we guessed these from nearby pits. And a deposition density of 450. That's just recommended by RAMs and kind of makes sense, really dense avalanche debris. So we performed a mass balance, basically. So mass released plus mass entrained, how close was that to the mass deposited? And we got an error of 4%, which I'm led to believe is pretty good. What else here? Oh, in B and C, we can take a closer look at that transect through our release area there. In B, we're looking at the snow surface elevation on May 17th before the slide, that's the darker line, and June 3rd after the slide. So we can see basically it diverges in the release area. It kind of reconverges at the cliff band that sort of acted as the Stolch wall. And then we can see it begins to diverge again, and that represents the onset of entrainment. In C, what we're looking at there is change in depth along that transect between the 2 days. So we can see some cracks that kind of held on. We can see it's really deep in the beginning of the release area, and then it kind of shallows as it reconverges to that cliff band, and then again, onset of entrainment. A couple other analyses we did with this data that I just want to briefly touch on. It's not quite as important, but first, we were interested in how terrain changes in snow-on versus snow-off conditions. So what we're looking at here in A is percent change in slope between the May snow-on scan and the October snow-off scan. What we're basically seeing is that, I mean, it's kind of intuitive, but spatial variability in snow depth is sort of altering the terrain slope in an interesting fashion. We're seeing a steepening of start zones between the cliff bands in the red, and slope reductions in the gullies where it's all piling in the blue, which makes sense. In B, if we look along this transect that's going down the slide path too, we look at pixel-wise slope distributions over here, we can just see a graphical representation of that. Basically, the slope along that transect is quite different when there's snow there versus when it's not. So what? Well, it's kind of neat. But also, with RAMs, again, one of the most important inputs is the terrain model, the sliding surface. So it would probably be wise to use a snow-on up-to-date DTM that actually represents that snow-on terrain in RAMs when possible. We also looked at changes in vegetation coverage, since that's another key RAMs input, is like forested regions that might restrict flow. By subtracting digital terrain models, which exclude vegetation, from digital surface models, which include it, we can make maps of canopy height, and this is all just stuff we can do with our Lidar data. What we see here is that basically in our study site, a deep snowpack and an early successional forest means that a lot of small trees become buried. So what, again? Well, buried trees are obviously irrelevant to avalanche flow, so it's probably a good idea to use an up-to-date canopy height model as your input to RAMs, which our TLS data is just great at producing. It didn't actually matter in this case because there was barely any vegetation in the slide path anyway, and our slide didn't make it there, but the point remains. All right, so now for the more exciting part, the actual RAMs modeling. We used our TLS-derived maps and quantities as key inputs. That's the top quadrant here. So we used the May 17th sliding surface. We used an up-to-date canopy height model. We used that average erosion depth that we knew of 0.7 meters. And most importantly, again, this is kind of the key input that dictates how much mass is in the avalanche, having an accurate estimate of release depth, or rather average depth in the release area, which we knew from our Lidar data was 3.3 meters. These parameters in the middle, we got from local pits, those 250, 350 estimates again, liquid water content of 10, snow temp of -1. That's just like ballparking for a late spring snowpack. These parameters down here relate more to modeling of friction in RAMs. All of those were either RAMs defaults or they were values typical of wet snow that were given to us by the RAMs team. So what I want to really highlight here is by tuning just a single parameter, this generation of random kinetic energy, which kind of dictates the flow regime, we were able to accurately model our slide and the runout extent here in A. So all these other values were just values given to us by the RAMs team, and they said for wet snow, you should alter that between 0 and 5 degrees. We found that with 1% we nailed it. So by tuning just a single parameter and using our TLS data as inputs, we were able to get an accurate depiction of this slide. The simulated versus actual deposition height varied by just 16 centimeters on average, which is pretty good. And so then, taking a step towards something more predictive, using these same settings, now that we had this model well-tuned, we incrementally increased the depth in the release area to see how deep it would need to be to hit the road. We found that critical depth was 4.6 meters, although I want to note that at 4.2 meters, I was starting to see the slide clearing the bench. It just slowed down just enough to trigger the RAM simulation to stop. But intuitively, looking at that terrain, I mean, like, that's like a waterfall. So I think if it clears the bench, it's probably hitting the road. If nothing else, for a factor of safety, we'll call it 4.2. And that also is in good agreement with the visual observations from the road the year that it did hit. They estimated that it was about 4 meters. Again, not as pretty as Alpine Solutions, but kind of neat. We can see our 3.3 observed one on the left stops where it's supposed to, 4.6 hits the road. So to conclude, we collected TLS data surrounding a large glide event in Glacier. We generated visualizations and quantified parameters of interest. We use these data as input for RAMs, much better inputs than RAMs usually gets. And then we tuned the model minimally to simulate the slide. Towards predictive forecasting, we increased the depth to see what the critical release area snow height necessary would be for impact at the road. In the future, going forward, we could use TLS again or something cheaper, like structure for motion, to try to determine the depth in that release area as the glide cracks form, and therefore the danger this glide poses to the sun road in the future. I really want to drive this one home. I think this method may be particularly useful for glide avalanches where we have a similar release area failing on a known interface, the ground, under similar snowpack conditions each year-ish, hence reduced need to retune the model. If we ran this exact same slide midwinter, we'd have to do everything all over again. It'd be totally different snowpack and friction conditions. We'd have to retune everything. But because of how much of like a repeat offender event glide avalanches are, I'm theorizing, hoping kind of, that this critical calculated depth might be kind of consistent and resilient from year to year. Follow-up observations would be cool. I do need to graduate at some point, though. Future work, though, near future, stuff I would like to put in this paper. There's a nearby weather station on the Haystack Saddle. It'd be cool to look at meteorological data leading up to the release and compare that to some of Peiche's old models for timing of these glide events, so we can comment a little more on that. And real quick before we wrap up, if you looked at the earlier agendas, there was some stuff that I was supposed to talk about with surface hoar mapping. I couldn't fit it at all, but we did a cool thing in the lab where we made classified maps of surface hoar versus any other snow type using near-infrared texture. We just submitted our minor revisions to Cryosphere. This will be published soon, and the preprint is available online if anyone was really dying to know about that. With that, I'll return to these to let them marinate, say thank you, and open it up for questions.
Yeah, really cool work, Jamie. Really interesting to see. Could you go back to slide 17?
Yep. This guy?
Or it might have been 16, the one that had all of your parameters for your model. Yeah, that one, thanks. I'm curious about a couple things. LWC and snow temp, those are bulk for the whole snowpack or for particular layers within the snowpack?
Ooh, good question. I'm guessing that's related to entrainment, so that's top layer, top okay. Meter-ish.
And when did you tweak any of those values just to see how those would affect your output versus the depth?
Not in like our formal analysis, but I've played with, just in general, like with the YC data and this stuff, I've tweaked everything quite a bit. It varies it a little. Wetter tends to run a little further, but again, the most important thing is the original mass that you're assigning to the slide. So depth in the release area is the main thing that makes it, yeah.
Awesome, great work, thanks.
Yeah, great job too. Jumping off that question, the RKE parameter, what physically influences that?
Damn it, Sam.
Oh, sorry.
All right, so it's the generation of random kinetic energy. Again, from my understanding, is you're pretty much defining the flow regime of the avalanche. Like a higher value, like 10%, is basically a fluid. A lower, like 1, is like really wet, slabby plug flow. What that actually physically is how much, what do they call it? How much granular movement of snow grains perpendicular to the path of flow there is at any given time. And it just, yeah, is it more dry, fluidy, or is it more chunky?
So it's both terrain and snow?
Terrain and snowpack are what dictate that, correct. And they recommended 0 to 5 for wet snow.
Just a question on the TLS products that you guys did. Is this just from one fixed exposure point on that glide crack, or did you guys use like multiple exposure points and kind of do a stereo model to build these mapping models?
I'm sorry, I missed that. Say again.
For like the TLS, were you just using one exposure point, or I know you mentioned maybe implementing structure for motion and continuing work on this. Do you think that would increase your accuracy or the terrain kind of depth of what you're seeing in startup zones, like being able to more accurately consider depths of starting zones?
What do you mean? I'm lost on exposure point.
Or just like one from, instead of pulling like two into a stereo model, like two TLS scans of a face together.
Mm-hmm. We had 2 scan locations, so for each individual outing, we had to pull 2 together. Yeah, and another note on georeferencing, we did have, this was thanks to Gabby, reflectors in the scene with GPS points on them. So that was kind of how we tie that all together. Did that kind of answer?
Yeah.
I think that rand kinetic energy, the parity work, it's pretty much a parity thing.
A lot of those are pretty much parity things.
Yeah,
from what I gathered.
that was, so I don't know where those come from exactly. Just to answer the question, it's not a typical parameter that you would find in some other engineering application. And there's been some controversy on just Perry's development of that.
I've heard snippets of that.
I was editor.
Is there a minimum snow depth that you will not see glide avalanches in those paths?
Ooh, I didn't tweak in that direction. I only went up. That's a good question, though. Because if you saw in that table, it fails like every other year. So conditions don't, sometimes it hangs on, or sometimes maybe it's just not deep enough. Cool. Thanks, guys.
Take a quick break, 10 minutes.